Hello teachers, welcome back to 7-4 where we're talking about the real numbers and irrational numbers. And I got cut off at the end of the last video, so I'm going to pick up right where we left off. And we're trying to evaluate these real numbers with rational exponents. And so remember, we defined 16 to the 1/4 in this is rational exponent form. We could write that in radical form if it would help us simplify. So you could write that, if you would like, as the 4th root of 16. That's one way you could do it. Now, you could break 16 down into prime factors. We know that 16 is actually 2 to the 4th power, because 2 times 2 is 4, times 2 again is 8, times the 4th 2 gives me 16. And notice, if your index and your exponent match, it's like they cancel each other out to give a result of 2. Now, another way you can handle it is you can leave it just like it is. Okay, so this is 16 to the 1/4 power. You could write 16 as 2 to the 4th to the 1/4 power. Now remember, what you do is when you have a power raised to another power like we do here, you multiply those together. So that would be 2 to the 4/4, which is just equal to 2. So 2 different ways to solve that problem. Now we could take a look at the typed up version, and notice what the book did is they did 2 to the 4th, and that's raised to the 1/4 power like we did. They didn't really explain it. 4 times 1/4 gives you 2 to the 1st, and that gives you a result of 2. So now that you know how to handle that, why don't you pause and go ahead and work B, C, D, and E and see if that goes okay. And if not, we'll work on this together. So what I want to do is take a look at 16 to the 5/4 power. Now, if we look at it like we did just a minute ago, we could rewrite 16 as 2 to the 4th, and then that's raised to the 5/4 power. Now again, exponent raised to another exponent, we can multiply those together. So that would be 2 to the 4 times 5/4. Remember, that 4 is over 1. When you multiply fractions together, you just multiply numerator times numerator, denominator times denominator. You are allowed to cancel numerators and denominators, so that's 2 to the 5th. And we know 2 to the 5th is 32. Again, it's okay to change that to radical form. If you decided to do it that way, that would be the 4th root of 16 to the 5th, or you could write it as the 4th root of 16 and the 5th on the outside. They're both correct. To me, the second way we wrote it's a little easier, because the 4th root of 16 we know is 2, and then the 5th we still have to deal with, and 2 to the 5th is 32. So which way is correct? They're both correct. Notice dealing with the fractional exponent in a way, though, is a little bit easier. And if we look at how the book typed that up, there we go. Now, let's do the next one. -8 to the 1/3. All right? So, can you evaluate this? This is the same as saying the cubed root of -8. Is that okay to do? You will tell me, yes, you can take the cubed root of a negative number. Now we know right off the bat that is -2. What if you left it as fractional exponent? That's okay too. You could write -8 as -2 to the 3rd power, and that is raised to the 1/3 power. And then you multiply 3 times 1/3, just gives you 1. So that's -2 to the 1st, which is -2 that way as well. In the typed up version, look, this time they wrote it in radical form. Why? I think they just wanted to do it a different way. You could do it with fractional exponents or rational exponents, or you could do it in radical form. For example, D. So we've got 125 raised to the -4/3 power. Now notice this is the first problem we've had in this section that had a negative exponent. Remember, the definition of negative exponents really means that belongs on the other side of the fraction bar. So this is the same as saying 1 over 125 to the +4/3 power. Now, we could write 125 as 5 to the third. If you break that down into prime factorization, that is 5 to the third, and that's raised to the 4/3 power. You multiply 3 times 4/3, the 3's cancel, that's 1 over 5 to the 4th, and then what is 5 to the 4th? And we know that 5 to the 4th is 625, so this is equivalent to 1 625ths, or 1 625ths. And there, let's see, I tried to show you the typed up version of that. There it is. Okay, very similar to how we did it. They decided to rewrite 125 as 5 to the third before changing that to a negative exponent. To a positive exponent. They did that step last. Notice the order that you do that in really doesn't matter. Now the next question, we have the 4th root of negative 16, right? Or negative 16 to the 1/4 power. Now, this one, it really helps a lot to rewrite that in radical form. We know that we can't do this. Okay, so this is not a real number. Why not? Because remember, anytime your index is even, okay, you cannot evaluate a negative argument inside. So that is not a real number, and there is the typed up version for that one. Now I've got a couple of homework examples to show you, and then we'll wrap this video up. So first homework example I've got going on here. Determine which of the following, if any, represent irrational numbers. We just need to know if these are irrational. My suggestion is take the value inside and factor it into prime factors. Well, you might sit with it for a few minutes, but if you try, you're going to realize that 43 is prime. You try to break it down. Remember, you don't have to go past the square root of 43 or the biggest perfect square. 49 is the next perfect square above 43, and so you would just have to check to see if 2 or 3 or 4 or 5 or 6 or 7 is a factor of 43, and none of those divide evenly into 43. Now, if 43 is prime, okay, that means it is not a perfect square, and therefore this is definitely an irrational number. On the other hand, question B, if you break it down, that's 7 times 7, that is the prime factorization, and the square root of 49 is the square root of 7 squared, and the square root of 7 squared is just 7, so that is not irrational, so I'm not going to circle it. Now let's check out question C. So 576, again, let's break that down into prime factors. I want to know what divides in there if I'm going to do a factor tree for this thing. 2 divides in there. We could just jump in with 2, and 576 divided by 2 is 288. That also is divisible by 2. So that'd be 2 times 144. 144 we know is 12 times 12. And 12 breaks down into 3 times 4, which breaks down into 2 times 2. That 4 does. So here we go. Again, 3 times 4. And 2 times 2. Now, let's highlight the end of the line here. So I got a 2, a 2, a 3, a 2, a 2, a 3, a 2, a 2. So if I were to write this down, 576 is equal to, how many 2's do we have? 1, 2, 3, 4, 5, 6. So that would be 2 to the 6th. And then how many 3's do we have? We have 1, 2 times 3 squared. Okay, now how did that help? Remember, we are taking the square root of that, and the square root of that is a perfect square. So the square root of 2 to the 6th, you can think about that as 2 to the 3rd times 2 to the 3rd. So that would be 2 to the 3rd. The square root of 3 squared is 3. Notice I'm just cutting these in half because that's 3 to the 1st. That's how you take a square root. 2 to the 3rd is 8 times 3 is 24. So 576 is not an irrational number because it is a perfect square. The square root of 576 is 24. Now, if you knew that right off the bat, you could just jump straight from here to here. But prime factorization is a good way to handle these big number problems. Now, let's keep going with our problem and work on D, which is the square root of 175. Now again, the idea is break this down into prime factorization. I know that 25 divides into 175, what, 7 times? Yes, okay. 25 breaks down into 5 times 5, and 7 is prime. So there's your prime factorization. So we could rewrite the square root of 175 as the square root of 5 squared times 7. Now the square root of 5 squared, because this is an even number, is 5 to the first times the square root of 7 has to stay underneath the square root because that 7 is not raised to an even power. Therefore, that is irrational. So I'm going to circle square root of 175. Now I'm also going to circle 3 minus 3 square root of 2. That is as simplified as it gets. And because there's still a square root of 2, because 2 is not a perfect square, that's an irrational number. Same thing for the next one over here. I'm going to circle that result as well, because 5 times the square root of 3 is an irrational number. I can't get rid of the square root of 3. It doesn't simplify at all. Therefore, we know we have an irrational number. So next example says to write each of the following in the simplest form as the nth root of b, where a and b are integers, b is greater than 0, and b has the least value possible. So we're trying to simplify the cubed root of negative 135. Now my first thought is, can you even do that? Can you take the cubed root of a negative number? And you would say yes. You can't take the fourth root of a negative number because that would be an even radical, and you can't do the even radical of a negative number, but you can do the odds. So this answer will be negative when we finish. Now my advice is to break 135 down into prime factorization like we did for the last problems. I know pretty quickly that 5 divides into 135. If we do the math, that's 27 times. 27 breaks down into 3 times 9. 9 breaks down into 3 times 3. So if I write this as the cubed root of, now notice we've got 3 3s, so that's 3 to the third times 5. Now, again, notice here, my index and my exponents, those are going to cancel each other out. So that's going to give me 3 on the outside. So I used up the cube root symbol around the 3 to the third, but I haven't used up the cube root symbol around the 5. That has to stay underneath. So that's the final result. Okay, what about the fifth root of 96? So once again, prime factorization here. So 96 divides by 2, and I get 2 times 48. Well, 2 is the end of that branch, but 48 will go further. And 48 will break down into, what, 2 times 24. 24 will break down into 6 times 4. Oh, I almost circled 6. We don't want 6 circled. 6 breaks down into 2 times 3, and 4 breaks down into 2 times 2. So there are the end of my branches, all prime numbers. So I could say the fifth root of 96 is equal to, I certainly didn't have to write it again, is equal to the fifth root of, now notice I've got 1, 2, 3, 4, 5 2s, so that's 2 to the fifth, and 1, 3, so times 3. Now once again, the fifth root of 2 to the fifth is 2, so I've used up my fifth root around the 2 to the fifth, but I have not used up my fifth root around the 3, so that is completely simplified. All right, how about question C? We've got the cubed root of 40. If I break down 40, that is, let's do 2 times 20. And 20 breaks down into 2 times 10, and 10 breaks down into 2 times 5. Into my branches, I got 2 times 2 times 2 times 5. So that's equal to the cubed root of 2 to the third times 5. Again, because if at 3 of these just leaves me with the 2. So the 2 comes out, but so I've used up the symbol on the 2 to the third, but I cannot use up the operation of cube root over the 5 because 5 is not a perfect cube. So that is completely simplified. And then our last problem, the fifth root of negative 1024. Now, 1024, prime factorization, what could we do? Let's do 1024 divided by 2. I see that one right off the bat. We have an even number. It's going to be 2 times 512. Well, 2 divides into 512 also 256 times. 2 divides into 256 128 times. 2 divides into 128 64 times. And you might know right off the bat that 64 is 2 to the 5th. So, wow, that's a lot of 2's, right? It's 1, 2, 3, 4, plus 5 more. That is 2 to the 9th power. Did I do that right? 1, 2, 3, 4. Oh, no, 64 is 2 to the 6th. My bad. So that is 2 to the 10th. So this is equivalent to saying the 5th root of negative 2 to the 10th power. Now, can we take the 5th root of a negative number? Sure we can, right? We can do odd roots. We can't do even roots of a negative number. So another way to think about this is the 5th root of negative 2. Okay, and you could say that's squared to the 5th, right? 2 times 5 is 10. So this 5th root and this 5th cancel each other out. So your answer is negative 2 squared. Actually, I need to be careful here with these parentheses, because when I put that square on the outside like that, that makes that turn positive. That's not really what's going on. So I don't need those extra parentheses inside, because we want that to be a negative 1024. So that's really negative 2 squared, not the negative squared, just the 2 squared. So that's going to give me a result of negative 4 is my final answer, because we know the 5th root of a negative number is a negative number, period. So negative 4 is what that's simplified to. And our last homework problem that we're going to go over together: in each of the following, find all real numbers x that satisfy the given equation. If none satisfy the equation, then state the answer is none. And I may or may not do all of these. We'll see. I do want to go through some of them, though. Get you used to this idea. So 5 to the x, looking at A, is equal to 3,125. Now, ideally, I need to write 3,125 as 5 to some power, okay? And you just might have to play around with your calculator and see how many 5s that is, even if it is some amount of 5. So I'm going to say 5 times 5, that's 25. That's not enough, right? Times 5 again is 125. Times 5 again is 625. Times 5 again is 3,125. So I believe that was 5 of them that I did. So 5 to the 5th power, yes, I checked it, is 3,125. Now what does that mean? Well, that must mean that x is equal to 5. For that to be true, that's going to have to be the case. So x is equal to 5 in that first situation. So that's A. Let's check out B. We've got 25 to the negative x is equal to 3,125. Now, we've already worked with 3,125. We knew that was 5 to the 5th. So let's go right back there, because I can write 25 as 5 to the 2nd. And what about that negative x? It's still out there. Now, notice we have a power raised to a power. That means I can multiply those together. So that's 5 to the negative 2x is equal to 5 to the 5th. Now, what do I do next? I set those exponents equal to each other and solve that algebra problem. So negative 2x is equal to 5. I divide both sides by negative 2, and x is negative 5 halves. Okay, let's see if I can get C over here. Okay, we've got 25 over 9 raised to the 3x power. On the other side, I have 243 over 3,125. All right. Now, we already know 3,125 we could write as 5 to the 5th, okay? And I see some 5s on the left, too. So here's what I'm going to do is just break this down as much as I can break it down. 25 is 5 squared. 9 is 3 squared. That 3x is still outside there. Okay. On the other side, 243 is 3 to the 5th power. Check it and see. And we already know 3,125 is 5 to the 5th power. Okay, now here's one thing I can do, because these are to the same power, the 5 to the 2nd and the 3 to the 2nd. I'm going to write this as 5/3 to the 2nd power on the outside, and that's still raised to the 3x power. On the other side, can I do the same thing? I can write that as 3/5 with the 5 on the outside. Now notice these are not the same, but if I could flip one of these, then they would be. How about we just flip the one on the right, and that's going to change that to a negative exponent. On the left, I still need to multiply that 2 times 3x because I have a power to a power. So that's going to give me 5/3 to the 6x power. And on this side, that's going to give me 5/3 to the negative 5 power. Now finally, I'm at the point where I can set this exponent equal to this exponent and solve. Now watch, I'm going to go to the top of the page. I'm just going to do this in orange so you can easily see it. So I have 6x is equal to negative 5. Set those exponents equal to each other. Divide both sides by 6 and you get negative 5/6 is the answer to that problem. All right, let's take a look at example D here. So we've got the square root of negative x is equal to 5 square root of 3. Now, I warn you about this. It looks like we couldn't do this problem because the left-hand side says the square root of a negative number. But remember, x doesn't necessarily mean that's a negative number. What if x were negative? Then you would have negative of a negative number. So you cannot have this if there's a value here. So you can't take the square root of negative 5 or the square root of negative 9. But when there's a variable inside, the variable could be a negative number to counteract this negative out front. So don't let that bother you. That can still be worked out. Now, what do we do to both sides here? Well, the advice is when you're trying to solve an equation that has a square root over the variable, you can square both sides like that. Now what's going to happen is it's going to give you negative x. The square root and the square cancel each other out. And on this side, I have to square both of these. This is a product, and any time you have a product raised to a power, you square them both. So 5 to the 2nd power, I'm just going to write down 5 squared. And you also have to evaluate square root of 3 squared. So on the left, I have negative x, and on the right, I have 5 squared is 25. The square root of 3 squared is just 3. The square root and the square cancel each other out. That gives me negative x is equal to 75, or x is equal to negative 75 if I were to divide both sides by negative 1. Okay, next, we've got x to the negative 5/9 is equal to 3. Now, just like we squared both sides when we have a square root, watch this trick. I'm going to raise this to the negative 9/5 power. Why? Because that's going to turn that exponent into a 1. And if I do it on that side, I also have to do that on the other side. So this negative 5/9 times this negative 9/5, that really is just x to the 1st, or x. Over here, you could just leave the answer like that. So 3 to the negative 9/5, I believe that's how the homework left it. When I did the homework, I left it like this. I said 1 over 3 to the positive 9/5 power. Is that the same thing? Yeah, sure it is. Okay. All right. And then example C. Let's see if I can squeeze it over here. So, I'm sorry, F. So we have x minus 1 squared is equal to 3. Again, if I'm trying to solve for this x, I could get rid of this square by doing the opposite of taking the square root from both sides. So I could write it like that, okay? But whenever you do that, you have to put a plus or minus in front of one of your sides. You could also raise them both to the 1/2 power. But again, keep in mind the plus or minus. So using the square root symbol, I remember to put the plus or minus a little better than if I don't put the square root symbol. So these cancel each other out. I have x minus 1 is equal to, now I have two answers here. One of them is positive square root of 3. The other one is x minus 1 is equal to negative square root of 3. Now what I do next to solve for x is I'm going to add 1 to both sides of the equation. So one of my answers is 1 plus the square root of 3. That's not going to give me the square root of 4, right? I cannot add a 1 and a square root of 3 by combining any like terms. That is just my answer. And when I add 1 to both sides on the next one, I get x is equal to 1 minus the square root of 3. And so there are two answers to example F. And that's the last homework problem that I want to do. If you have any problems with this section or any others, please let me know. And I hope you have a great day.